Hello, everyone, and welcome to another meeting of our reading group. Today, we are excited to have Oriol Nieto from Adobe Research. He's a senior researcher engineering at Adobe. And as always, if you have any questions, feel free to raise your hand and ask the question directly to the speaker, or you could write your questions in the chat. Without any further ado, the stage is all yours.
Great. Thank you, Puna. It's a pleasure to be here talking about some of the latest research we've been doing at Adobe Research. And yeah, I'm going to be focusing on sound design today. So what is sound design? We can define sound design as the art and practice of creating audio elements for various media, including films, television, video games, theater, etc. And a big component of sound design is coming up with ideas to map specific sounds to the creations that you've been working with. And I'm just going to let an expert Foley artist talk about it instead of me.
These are actually just toilet plungers.
Meet Joanna Fang, Foley artist for PlayStation Studios and a master at sonically translating our world through works like God of War Ragnarok.
So as we can see, it can be extremely difficult to have access to so many props and recording gear and come up with all of these high quality sounds. And moreover, there's a big component of sound design that entails having to carefully tune so many knobs and presets to synchronize the final sound to a given video, or just to create like the perfect sound that you want for your creation. And this can be quite daunting and tedious. And we believe that with the help of AI, we could help all of these creators to have a better experience and to spend less time on this tedious task and spend more time on the creative aspects of their work. And that's where the Sound Design AI group, or SODA, comes in. This is my group at Adobe Research, and this initiative started like a year and a half ago, more or less. We're only 3 researchers. This is led by Justin Salomon, and then Prem Sitharaman and myself are the main researchers in the team. Then we collaborate with a lot of interns, especially during the summers, and thanks to that, we produce a lot of papers, and then some of the work ends up going to the product, and it's quite nice to see people talking about what we've been doing in terms of like the product. They're playing with the models and giving us a lot of feedback, and it's great to see the models in the wild. And as an example, I'm gonna show some of our latest additions to Premiere Pro, the video editing tool by Adobe. This is Generative Extend, and just 2 weeks ago made it into general release. So this is all available to the public. I'm just gonna play a little video of what this does.
You're in the middle of editing when you find a clip that you wish were just a little longer. With Adobe's new Generative Extend, you can now generate extra frames to perfectly fill the gap. For example, I have a clip here that I want to make a bit longer. Watch how I can extend it by dragging the end over here. Let's give it a few seconds to process, and just like that, new frames have been added, and you won't even notice where the AI steps in. Generative Extend also works on audio. I had an audio clip of people clapping that felt a little too short, so I extended it, and just like that, Premiere generated more applause that matches the original audio. This feature is currently available in public beta, which means you can already use it yourself, so make sure you give it a try.
Yeah, this is no longer in beta. This is already in the main product, so it's really cool. We were at this. Yeah, it won some awards. Yeah, I don't know, it's crazy, but yeah, it's really cool to see like models that we've trained using our little environment, and now they're out there in the wild. So it's pretty gratifying. Anyway, so this is what we do, and this is where I come from, and now for the focus of the talk, I'm gonna give a very high level, basically like a little perspective of what diffusion models for audio generation do. to kind of set the tone, and this will help me to talk about 3 different projects. The first one is Sila, the second one is Sketch to Sound, and the final one is Multifoley. These are 3 projects that we've done in the past few months at Adobe Research. So I'm going to start with setting the tone with the diffusion models for audio generation. So apologies if all of this is very familiar to you. I just want to make sure that we're all kind of on the same page. But imagine that you have this model that will be able to generate any type of sound unconditionally. You sample from it and you generate high quality sound. And this will be our diffusion model. Imagine this is already trained, so you can just sample from it and you'll get a sound. Now, what we usually do is to condition these models. And usually the condition is just by text. So you use a text prompt and then you condition the model and you output the sound that pretty much matches the description of the text. Now, these diffusion models, what they take is pure Gaussian noise. So if we're operating in the time domain, and let's say that this model generates 10 seconds of audio, then you put 10 seconds of pure Gaussian noise in the time domain. And what this model is going to do is try to denoise, like de-diffuse the Gaussian noise into several steps, such that at the final step, you're going to have high quality sound. Now this high quality audio is very high dimensional. All the examples that I'm going to be giving today are 48K. So that means that in 1 second of mono audio, there's going to be 48,000 samples. So this is very high dimensional. So usually the way we operate here is to use latent diffusion models, which means that these diffusion models are going to be operating in the latent space. So now the output of the model is this latent representation, or this kind of feature embedding that then we can decode using a pre-trained decoder to bring it back to the time domain. And now, since we're operating in this latent space, the Gaussian noise is going to be 2-dimensional because that's the representation of our latents. But this latent is going to be much more compact. It's going to be 40 hertz instead of like 48,000. It's not that big of a difference, like that many orders of magnitude, because it's 2-dimensional, but it's still like several orders of magnitude more compact. So the diffusion model will be able to work much more efficiently. Examples of the encoder-decoder that are typically used for audio are like variational autoencoders, residual vector quantization. DAC here is the direct audio, the script audio codec, and that is completely pre-trained and open source. You can just get it off the shelf and just use it right away, open source. Okay, so imagine that this is already trained. Once this is done, you can just sample from it. You just put like complete random noise, and let's say, for example, that you put in your text waves crashing on a hill in the ocean. The output would sound something like this from one of our models. Or lion roaring. Okay, so how do we train these models? To train these models, we have a data set of pairs of audio, high quality audio, and descriptions of this high quality audio. And then you just, for the text prompts, for the text branch, you just condition the diffusion model using your favorite text encoder. We typically use T5. And then we pass the audio through the encoder of your choose. We typically use VAEs, and this is all pre-trained. The encoder and the decoder are pre-trained, so that we get the latent. And now with the latent, what we do is to pass it through what is called the diffusion process. And the diffusion process is basically going to take a noisy latent, a completely Gaussian latent, and basically add this noise into the input latent. Such that the diffusion model during training will see a noisy version of the audio. And what it's going to try to do is to basically remove all the audio, de-diffuse or denoise the to diffuse all the noise so that you will get the latent that is clean. So you can just think about it as taking the mean square error of the initial latent before adding the noise and the denoised latent. All of this is much more complicated. There's like a lot of math behind it. There's so many techniques in the past few years that allow this to be way more efficient and do this in less steps, but this is kind of the high level. We only train the diffusion model. The diffusion model can be UNet conditioned on the text prompt. It can be diffusion transformers. We actually use diffusion transformers in all of the works that I'm going to talk about today, but that's not really that important. I'm just going to give this high level perspective of this. Now, one of the key things is that during training, the denoise process only denoise a single step, so that this way you can just build these batches very efficiently, so that you can train at really large scales. And during inference, you will just denoise from Gaussian latent, and you will have to go through all the steps. And that's why these latent diffusion models or these diffusion models can be a little bit expensive. And as I said, there's so much literature in the past few years. There's been like almost like every month there's like something new that makes the number of steps way smaller, and this becomes more efficient. So the rate of progress here is insane. But yeah, hopefully now we're all on the same page in terms of audio diffusion models. And I can start talking about the first project, that is SILA. And SILA is signal to language augmentation for enhanced control in text to audio generation. And this is a work led by one of our interns, Sonal Kumar. And the motivation is that text-based models have limited control, and it's usually hard to obtain the desired results, right, with just a single text prompt. You usually want a little bit more fine-grained control. So can we add this control with minimal impact in architecture and performance? And that is exactly what SILA does, and yeah, it's enhanced control in text to audio generation. So back to our training framework for diffusion models for audio. Now we're just going to focus on the initial training part, and this is just an augmentation process that we are proposing, the SILA paper. So what we do is, given our pairs of high quality audio and the text describing the high quality audio, we add a little module that we call DSP enhancement. DSP stands for digital signal processing. And what we do is to basically analyze the signal, and depending on that, we will come up with an enhanced audio version and an enhanced text prompt. Once we have that, and this is just for augmentation, we just continue as usual. And the DSP enhancement, we propose to use loudness, pitch, reverb, noise, brightness, fade in, fade out, and duration. And this, what this DSP enhancement component actually looks like, this is the signal to language part of the paper. I'm just going to exemplify it with this. So imagine that you have this signal as input. And in the description of this, in your training set, you have a prompt that says a thunder echoes through the sky. So we pass it through the DSP enhancer module, and we see that the volume of the signal, the LKFS, is -10, and that is a pretty loud signal. So what we do is to just add just some text to the original prompt. So we just concatenate loudness, very loud, to the original prompt. Now we go and check for brightness. We check the spectral centroid of the audio, and we see that it's 65, and we consider that to be pretty bright. So we add brightness bright. In terms of reverb, we decide in that process, in the augmentation process, that we want to add a lot of reverb. So then we just concatenate the string reverb very wet, and we just keep doing this again through the training process. The analysis of the signal or the additional of reverb or fade in and fade out is super cheap, so we can do this just on the fly. And these rules that we that we are describing here, like if it's minus 10 LKFS of volume, that's very loud. We come up with them based on the distribution of the data from our data set. So it's not like hand wavy. And basically, once this is just done, the final prompt will look like a thunder echoes through the sky, and loudness very loud, and brightness bright, and reverb very wet. And the final signal in this case, as an example, will have a lot of reverb. I'm just gonna play it for you. Okay, and that's it. Basically, once you train like this, you have a model that is conditioned by text and generates audio that has the ability of understanding all of these more nuanced audio characteristics. We ran a perceptual evaluation with 22 subjects, and we compared our model with several other state-of-the-art models from audio and sound effects generations. And we analyzed how well they were able to produce some of these audio characteristics that we propose in the paper. And basically, none of them are able to understand what it means to make the pitch brighter, to add reverb or noise. But if you just add this little trick, which is extremely efficient, then suddenly your models will understand all of that. As some examples, once the model is trained, let's say that you have deep rumble of the storm echoes through the sky and loudness soft. And if you do the same with loudness very loud, it would sound like this. So I really love this example because it's telling you that, hey, loudness is not just a knob of gain, right? Loudness, the model, what it understands is semantically meaningful. If you say like a thunder, the sound of thunder, but soft, it will understand that it's going to be kind of far away, and the high frequency components are going to be pretty much gone. So you will only hear the low frequency ones. Whereas if it's very loud, it's going to be so much closer to you, and the high frequencies are going to be present. So it kind of understands the semantic meaning of what you're trying to produce in the audio. Another example: a dog barking nearby and reverb dry, and the same with the reverb wet. Okay, so to summarize Sila, we added control across several acoustic features. It's highly efficient, no added computation during inference. Also, you don't need additional training data, right? All of this comes from whatever training data you have. You just analyze it with standard DSP techniques. And it's model agnostic. As long as you have an audio generation model conditioned on text, it doesn't matter if it's diffusion or it's autoregressive, or I don't know, GANs or something, you can just apply these. Okay, so the second work that I wanted to talk about is sketch to sound. And sketch to sound is controllable audio generation via time-varying signals and sonic imitations. And this was led by one of our interns. This is Hugo Garcia Flores, and yeah, he did an incredible job with this. We just presented this at ICAST 2 weeks ago in India, and it was pretty well received. So the motivation is that text prompts can be quite limiting, even with the Sila standalone addition that I just talked about. The problem is that there's lack of fine-grained control expression, like where in the generation do you want it to be louder or quieter, etc. So can we control the generation via audio? And that's the audio is the time-varying signals. You can think of it as a time-varying signal, and you can do the imitations. You'll see why this is called like that. So we're back to the training framework of diffusion models. We're just going to focus on the first part like before. And I'm just rearranging things a little bit to give a bit more room. But this is the same strategy that I discussed before. And now just going to show a real audio signal. This is just the Mel spectrogram, or basically the spectral of the sound. And what we do is to analyze the signal to obtain 3 characteristics of the signal in terms of time varying signals. These are the time varying signals, and we are focusing on 3 different ones. We're focusing on loudness, we're focusing on the spectral centroid, and we are focusing on pitch probability. So we extract all of these, and what we do is to pass them through a median filter to adjust for potential outliers or sudden changes. If you want, you can have a longer median filter or a smaller median filter, depending on how much granularity you want. And what we do once you pass them through the median filter is to basically add this linear projection, this little MLP, on top of each one of these audio characteristics. And this is pretty modular. If you want to add more signals, you could add it. And now the main idea here is that we add these outputs of these time varying signals to the noise of the diffusion process. So instead of having Gaussian noise going to the diffusion process, now the Gaussian noise will be a little bit conditioned. You can think of it as having some sort of a prior going to the diffusion process, so that we're already guiding the diffusion process to go to a place that hopefully will allow the output to match the loudness, centroid, and pitch probabilities in our case to the input. Now, this you can just do as a fine-tuning process. So once you have your diffusion model trained already, you can just fine-tune it on a single GPU for 40,000 iterations, and that's it. So it's pretty cheap, and there's no need of extra training data, right? Like this, in this case, you don't need any special type of data in order to do that. You use your whatever data set you have, you just extract these time varying signals, and you obtain something that will allow you to do something like this. So there's a little demo once the model is trained, and you'll see here Hugo doing some audio imitations with his mouth, with his voice, and then you will hear the result of the prompt once you modify it and pass it through the network. Okay, so, yeah, this video went viral on Instagram. Someone reposted it, and it was like millions of views. It's kind of crazy. Justin was like, I should have done my hair if I would have known better. Anyways, to just illustrate that this works for other signals rather than just voice. So here's Hugo playing guitar and using the output of the guitar as the input to the model. So I really love this work because it kind of brings back the performer into the Foley generation, right? And that's kind of the heart of the whole thing. And kind of what we do is try to bring back the kind of the expressivity, allow the human to express whatever they want, and to just have the machines help them, like then tune the little sound at the end. Okay, just some insights about sketch to sound. as I said, we add a median filter, and what we did is just see what happens with different median filter sizes. And these are some of the metrics that we analyze. We analyze the clap score, we analyze the Frechet audio distance, and we just compared some of the audio characteristics differences. So we have the pitch error and the loudness, the RMS error. So we see that if the median filter is smaller, then the sound is going to be more precise. There's going to be more adherence into the loudness, more adherence to the pitch. So these time variant signals will be more similar to the actual input. And on the other hand, if the median filter size is larger, there's going to be more sketch-like. It's going to be a better audio quality, and you're going to have better text adherence. So the final result will actually be closer to the text prompt that you're trying to do, even though maybe the fine-grained qualities is not going to be so close to the input. And yeah, the median filter size is completely randomized during training, so that once the model is trained, you can basically just tweak the median filter as you want during inference. Finally, the semantics of control curves are implicitly modeled, and that's a pretty cool observation that we found once all of these models were trained. So imagine that you have this input. And in the text prompt, you type forest ambience. The model will understand that the whistle sounds will have to be birds, because that's the most likely component of what's going to happen here in a forest, and it kind of knows that the whistle sound very likely is going to be birds in the forest. And note that we are not saying to produce birds here. And the final example. It's pretty cool when you just say bass drum and snare drum. It will understand based on the sound, on the pitch sound of the or non-pitch sound of the input, whether to use a snare or a bass. And the less pitch sound is going to be the snare, as you will hear, and the more pitch sound, as you can see this, is going to be the bass. And it's really cool that even like the toms of the drum are kind of matching the pitch of the input you'll hear. All right. So just to summarize, sketch to sound, we added control generation with audio and fine-grained control. Like you can just input any audio signal and it will adhere to this audio when the generation sound occurs. Then we keep the human in the loop, right? Like we bring back the performer here, expressive vocal input or any type of audio input, and you can tune the type of sketches using the median filter, which makes it even more expressive. And it's a very efficient method, right? It's model agnostic. You don't need additional training data, and you can just use it as a fine-tune in a single GPU for 40,000 iterations. Okay, so that's sketch to sound. And finally, the last project I wanted to talk about is Multifoley. And Multifoley is video-guided Foley sound generation with multimodal controls. And this was led by Ziyang Chen, and this is going to be presented in a month or two at CVPR. And yeah, this is perfect synchronization with video that can be tedious, right? So can we actually use videos as an additional condition for the generation? And how about we combine text, audio, and video, and we just put it all together? Okay, so back to our training framework. We're just going to focus on the first part again. And now I'm just rearranging stuff like the text branch and the audio branch is going to be exactly the same, at least for now. And now we have a third modality, and these are videos. And in this case, the videos, what we do is to get another encoder. We use CAVP from the DeFoley paper, so that we obtain video latents. And the video latents are sampled at a different sampling frequency than the audio latents. So what we need to do is to basically resample so that they can match. Once the video and the latents, the video latents and the audio latents are matched, we can just concatenate them, and we actually just concatenate them across the channels dimension of the tensor, so that we just still have a valid tensor. We're just adding some dimensions through the channels. And once we do that, basically we just train as usual, right? Like the audio encoder and the video encoder are completely frozen. We just train the diffusion model. And the video latents are masked during the diffusion process so that we do not generate video, right? We are only focusing on the part of the audio. And that's basically the whole technique. And once this is trained, there's a lot of details in the paper about classifier-free guidance. We do a lot of trying to generate high-quality audio sound from a low-quality video data set. But I'm not going to go into details here. But yeah, if you're more interested, just read the paper. But yeah, I'm just going to show some results that we got. So now imagine that we have a silent video of this bird, and we just condition the model with bird chirping. Now we just put together the video, and you'll see that the sound is synchronized to the video completely. But we can get creative with this. So instead of bird chirping, what if we just say rooster crowing? I also love that it understands that we're outside in like a forest or something, and you can also hear the ambience of the wind and stuff. Anyways, well, what if you put like male speaking here? Or sheep bleating, I don't know. Okay. I'm not sure how synchronized this is going through, but this example really shows how really well synchronized the video and the audio are. So if you just have a typewriter, you would get something like this. And just for fun, what if you just, instead of typewriter, use piano? Or just a keyboard. And here we have another example with a cello. I really like this example because the model kind of understands that if you move your left hand across the neck, you're going to change pitch. It doesn't really know whether it should be higher or lower, but it kind of does change the pitch. Also when you change the fingers, so it's pretty good at that. But it really knows that when the hand is moving slightly, doing the vibrato, it adds the vibrato to the sound. So that really captures it pretty well. But yeah, if instead of cello you put an heru, this is what it would sound. Or a chainsaw, so crazy. Love it. It keeps changing the pitch. Anyways, and just to illustrate that this works for all other types of modalities, I'm just going to show this little video, right? Like if you give the reference of a dog bark, then it will synchronize that type of sound to the video so that you don't even need to use the text prompt. Okay, so yeah, this is the multi-Foley, a method to generate audio from video. It has multimodal control. It has audio, video, and text. It has high quality output even when trained on low quality video dataset. As I mentioned briefly, this was trained on a low quality video and audio dataset. That's VGG sound. And what we did, so that was the only video dataset that we had available. Video with audio, right? So what we did was to do some classifier-free guidance with a high-quality audio-only dataset in order to train this, and that's why we were able to basically obtain really high-quality audio at the end. But yeah, I encourage you to read the paper if you are interested to know more. And that's basically it. As closing remarks, I presented SILA. It's basically enhanced text control, sketch to sound, so added voice control to these generations, and multi-Foley. So now we can use video, text, and audio control to these sound effects generations. And I believe that the future of sound design will be drastically shaped by AI, but rather than replicating sound design artists, I believe that such models will actually assist these artists, allowing them to expand their expressivity and creativity, and helping them in spending less time working on tedious and dull tasks, and spending more time into expressing themselves. But yeah, let's have our professional Foley artist Joanna Fang talk about it.
Joanna's mastery of her craft is unique, and even in the digital age, she feels the role of a Foley artist is still vital to storytelling.
I can imagine a future where machine learning aids us in Foley, but I do not ever believe that it will take away the simple and beautiful performative nature of it.
Okay, and just for references, I can share the slides with you, Pune, so maybe you can put it on the website. And yeah, and that's pretty much it. Here you have some QR codes to the actual papers of each one of these projects. And with that, yeah, thank you so much, and I'll take any questions.
Thanks a lot. It is like very interesting and at the same time very fun. It is like watching something very fun for me. Thanks a lot. So
Thank you so much.
if everyone has any questions, feel free to raise your hand to ask the question or write down your question in the chat. So maybe I could start with something. So like the quality of all these models that you have shown is like perfect, I guess. It's very good. So how much data is required to train such models? Like,
yeah, so we have at Adobe, we have licensed several data sets for sound effects, and we have basically, in this case, we have around 1 million different sound effects. I forget the number of hours, but this might be, it was around 10,000, between 10,000 and 20,000 hours of sound effects. You don't really need that much to have like a model that sounds already okay. And there's like a lot of open data sets out there, like free sound audio sets that you can already use, and these are pretty big data sets. But these data sets are typically not that high quality, and we can't use this data to put that into product because of legal reasons, of course, and ethical reasons. So we are very careful at Adobe to just, you can use like licensed data that we have purchased and for generative models. And in that case, yeah, this like the ones like for the model that we put out there in Premiere Pro, they were only trained on super high quality data that we just had licensed. For some of these examples that they are only in the paper, they're not in any product. We used parts of free sound, for example, that adds a little bit of more noise to the data, which actually helped a little bit to regularize the whole thing. But yeah, like around, yeah, if you have like around 10,000 hours, you should be good. Yeah. Okay,
nice. So there's one question in the chat. Would you recommend diffusion for other audio related purpose, like musical audio denoising?
Yeah, that's a good question. For denoising, it probably would work. Like we actually have a paper in 2021, and it's one of the first papers that I've seen in audio using diffusion models, and it was exactly doing that. Like trying to denoise a music signal that was a bit noisy. But back then, it's crazy. It's only like 4 years ago, but 4 years ago in the machine learning community is like eons ago, and we use like a different way of having we didn't have like a latent diffusion model, even though we were operating in the Mel spectrogram, and then yeah, but it worked. Like you can, if you have the training data, you can do something like that. Like diffusion models, the problem of diffusion models is that they can be expensive, and you usually need a beefy GPU to be able to do inference. But they are very good at matching the desired probability distribution that you're trying to get at, as opposed to something like GANs that they typically just try to get the mode of the data. These diffusion models are really good. They become like really good at obtaining this really high quality audio, and getting really to the distribution, the probability distribution of your input data. So yeah, they're pretty powerful, and I'm sure that even for other tasks, right, like for speech generation and for music generation, not only like denoising, could work very well. And again, this is machine learning. Now kind of autoregressive models are kind of coming back, and now a lot of people are doing autoregressive and diffusion at the same time. And maybe in a year or two, there's going to be the next big thing that is going to be completely different. But for now, these diffusion models, and now maybe like adding some autoregressive on them, like combining with some sort of a transformer architecture, is kind of like the state of the art.
Perfect, thanks. I know, Mirko, you want to ask a question, yeah?
Yeah, actually, that was my my question regarding the autoregressive generation, because it looks like people are like getting even more inter like you got very good results, right, with diffusion, but people started to like resume a little bit autoregressive generation, right, because they're of their better compatibility with the multimodal LLMs, right? So I'm wondering what's your opinion on that, about like autoregressive generation with audio tokens, for instance.
Yeah, I believe like in our case, it made a lot of sense to use diffusion, because we mostly are not that interested in generating long audios because of the nature of sound design and Foley. We typically operate on shorter audio signals. But I can see like something for like music, autoregressive models that we can just like keep basically sampling from, might make more sense, even though I'm not really that familiar about how they generate like these music models, like 5 minutes of music, but I believe having some sort of an autoregressive mechanism will help a lot, right? Like if you maybe you generate some part of, like, I don't know, like a minute or 30 seconds of audio using a diffusion model, but you can actually represent it as several tokens that can be fed into an autoregressive model that will generate the next ones, that then they go through the diffusion process and generate the next ones again, so that there's some sort of coherence between what you have generated and the next section of the music. We did this because we were exploring the diffusion models, and we saw that from the initial explorations, they were working really well for sound effects. But it's not that we are fully married to that, right? Like maybe we're gonna start. Actually, we are interested in kind of combining the two of them, and this summer we might actually start exploring this. And there's like a lot of people at Adobe Research, like kind of playing with both of them, or even like trying something new. Yeah, I'm not saying that diffusion models are what everyone should be using. It's just that right now we managed to make these diffusion models work pretty well, but we'll see what happens in the near future. Autoregressive models are pretty amazing.
That's really great, actually. Yeah, so interesting, like finding proper ways to combine diffusion and autoregressive generation, and yeah, I think will be really even more interesting to find a way to combine the two modalities, like diffusion and autoregressive, just like have a framework which is signal agnostic, which can work for audio, can work for text, can work for everything, right? That can lead to the next generation of multimodal LLMs where you combine audio, text, and video, right, with diffusion and autoregressive generation. Yeah, that's really interesting. Yeah, thank you for those, by the way. That's very interesting. Yeah.
Thank you. Thanks for the great questions. Thanks.
Okay, final round of question. Is there any other questions? Okay, maybe I could ask one final things for the last model that you present, Multifoly. So there's the example that is a bird and then you pass a prompt like male speaking, but basically there is no actual speech. So have you tried something like having also the text, the actual text that the speaker could talk and see what happens?
Yeah, no, it doesn't work. We don't have speech data in the training set, so it doesn't really know what to do. Yeah.
I see.
So I don't know if we tried adding like that, but you know, we tried just as input people speaking like a conversation, and they just it's garbage. It's just it's something that you hear humans talking, but it's not really something comprehensible, but something that makes sense. I think maybe if we have like the right type of data, and with actual transcriptions of what they're saying, it might work. But yeah, our training data didn't have this.
I see. Thanks. I think we are done with all the questions. Thanks again for joining. It's a really great talk. So for next week, we have Daniel Povey. He's going to talk about consistency regularization and CTC for improved speech recognition. Thank you everyone for joining and looking forward to seeing you all next week.